Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, or this week, we're going to start looking at trusses. Now trusses are very important because they're going to be the first question you see on the final. In all of the years past, trusses are usually the first question, bending and shear moment diagrams are second, friction's third, and moment of inertia is fourth. So when we're looking at the final, trusses, this is going to be number one. Now, trusses are incredibly simple, but also incredibly dumb. And the reason why they're dumb, as you're going to see, is sign convention. Solving trusses does not take a lot of effort. In fact, you'll see that most of it is actually just a combination of two things. The first is going to be support reactions, which we learned last week. So it's going to be very, very important that you know how to find support reactions of a simple structure. And then the second thing is going to be particle equilibrium. So if you think way back to, I believe, week 3, that's when we covered particle equilibrium, which is when all those forces that are on a body act at a single point. So basically, instead of having the 3 equilibrium equations that we know for 2D, we have 2, because if they all act at the same point, none of them are going to create a moment about that point. So what you'll see in trusses is we treat each of the joints in a truss like a particle equilibrium. Everything acts at that joint or that particle. So we can solve for those forces using 2 equilibrium equations, which are some of the forces in the x and some of the forces in the y. But what you guys will later see is sometimes we won't be able to solve a joint. And what we'll find using this method of joints is we're going to go through each of the joints and we're going to solve for all the unknown forces in a truss. Now, the order at which you pick the joints is going to be very, very important, because as you guys will see, if you pick a joint, let's say right in the middle of the truss, and it has 4 members in it, all 4 of those members are going to be unknown. So with that being said, we only have 2 equations, so we can only solve for 2 unknowns. So if there's 4 unknowns, we can't actually solve that joint. However, what you guys will see is there's some joints that we can solve. And if we solve those joints, then we can actually move on to the next joints and then solve those ones, and then so on and so on. So it's very important where we start. And usually you're going to want to start at a support. And that's why we need to know the support reactions, is because if we're starting at the support, those reactions that are at that support or at that joint because of the support, they need to be accounted for. So this example will be kind of a shorter example just to kind of get you guys warmed up to the method of joints. And then in the next example, I'm going to do a second one using the method of joints, a structure that's maybe a little bit more complex. But the nice thing about trusses is it's actually an incredibly simple unit. If you guys are very, very aware of your sign convention. And I'm going to show you my sign convention the way I like to do it. And if you do this way, you'll never mess up. When I taught the lab for this a year ago and then 2 years ago and so on, I find that every student knew exactly what to do. The only thing that would mess them up are them switching their signs. And as you guys will see, for trusses, there's going to be a lot of members. Sometimes you can very easily get confused and switch up a sign. And if you switch one sign, so let's say something is positive and you switch it to negative, it's going to mess up your whole truss. So it's very important that you have a standard sign convention. And again, I'll show you which one I use. And from there, we can go on and hopefully you guys can stick to mine, or if you guys believe that your guys' is the best, then by all means, go for it. That's whatever you guys are more comfortable with. But my method works. Your method may not work. I'm not saying it won't work, but just make sure it works, please. The worst thing that you could ever have is when a student comes to you and says, I know my truss is wrong, I don't know where it is, and then they show you calculations for 10 members and you don't even know where to start. And it's usually, like I said, it's just one negative that swaps everything. All right, so that's quite the introduction to trusses. The best way to learn is just to start going through them. So that's what we're going to do now. So sit back, relax, and let's begin. Alrighty, so looking at this example, it would like us to determine the force in each member of the truss, and this is very important, and state if the members are in tension or compression. So real quick before we finish up what else this question would like us to do, this second statement here, state if the members are in tension or compression, is very important for trusses. Now, as you guys will see a lot in the textbook, they'll explicitly ask you, state if it's in compression or tension. Now, from what I've seen in the labs, usually we'll ask you too in the labs, state if it's in tension or compression. But here's something that you guys should know. This statement shouldn't have to be said. So if you guys are doing a truss question, let's say in the final, and it doesn't say state if the members are in tension or compression, you guys should know in your heads, I should do this anyway. because if it's in tension or compression, that's a big deal. Think about if you're designing a truss. If a member is in tension, we're going to have to design it one way. If it's in compression, we're actually going to have to design it a different way. And the ways are actually very similar. There's just some things that you're going to have to take into account for each of the sections. So the fact that it's in tension or compression, that's actually a big deal. So even though it may not ask for it in some scenarios, you should do it anyways. So that's kind of the first hint. And then the second thing says set P1 is equal to 20 kilonewtons and P2 is equal to 10 kilonewtons. So when I look at this diagram really quick, we know that we have P1 at the top. Oops, that is not what I wanted to do. So we know that P1, this one's actually equal to 20 kilonewtons. And we got P2 at the bottom, which we know is equal to 10 kilonewtons. So we have a nice truss here. It's actually pretty simple. It wants us to determine the forces in each one of those members. So we're going to have to find the force, and I'm just going to highlight. So we're going to have to find the force in 1, 2, 3, 4 members. So if this is the case, like I said, there's two methods. The first one we're going to cover, though, is method of joints. It's kind of the simpler method, mechanics-wise, where it's not very complex, but it could become very tedious when your structure is quite a big structure. One thing that you guys will see is if we had a very long truss, and I'm trying to find just one of the forces, let's say right in the middle of the truss. Method of joints will actually become very, very tedious, and you won't want to do it. And that's when we go to the second method. But we're not going to cover that yet. I'm going to save that for a little bit later. As you guys will see, it's lots of fun as well. And that's called the method of sections. But we're going to not cover this. So the first thing that I want to kind of discuss when the method of sections is all we're going to do in this method. Oops. The only thing that this method is about is we take each of the joints of the truss and we analyze them as a particle equilibrium. That's all this is analyzing joints in a truss. And the best way to describe it would probably be, remember cables. If I was having a free body diagram at C, and instead of those being truss members, we'll pretend that there's two cables there. Remember when I say I did a free body diagram, I would just circle the particle. So in this case, this would be my particle. And if I were to draw a little free body diagram on the side, I draw the particle. And I go, okay, well, I got a load on this particle coming down. And this load will be P1. And remember what I said about particles. I said, particles. Remember what I said about cables. If we cut a cable, which we did here, so if we look at this truss, we cut the cable at 1, 2 spots. We're going to have to replace those cables with a force because we cut through them. And those forces will always be in tension. So in this free body diagram, I'd have one force coming this way, which I would call, let's say, tension 1. And then I would have a second force coming down, which should be tension 2. And then from this free body diagram, I can use my sum of the forces in X and the sum of the forces in Y to solve for T1 and T2. And in this case, it's actually very obvious what each one will be. But now here's kind of the little trick. And that is a truss member is actually very similar to a cable in that if I cut it, it's only going to have one force, and that's going to be along its line here. So if I were to cut that, that would have an axial force there. If I were to cut this one would have an axial force coming up like this. But the only trick that you guys are going to have to remember, and that's going to be very, very important, is that unlike a cable, a truss member can be in compression as well as tension. So there's actually two scenarios, and this is where it's going to create all the headaches for you guys. Because remember, in cables, if we had them and we cut through them, this would be the free body diagram on this side, and that'd be the correct way. Remember, tension always points away from the particle. But now we're in kind of a unique scenario where it doesn't have to point away from the particle. If T1 was in compression, the actual force would look like this, where it'd be coming in. And that's completely valid. It just means that the member is in compression. So now we have to ask ourselves, okay, well, we have a problem. I don't know if it's in tension or compression. Like, sure, you guys can look at the structure, and based on the loads, you guys can probably actually make a pretty educated guess. But we don't know. So it kind of goes back to support conditions. We don't remember, or not remember, we definitely remember support conditions, but we don't know which direction they're going. If I had a roller, I don't know if the roller is going to be pointed up or pointed down, the force. So now we're going to have to kind of go back to something which I know all of you guys love so much, and it's going to become such an important part of all your careers, and that is called assuming. And you would think that with engineering, as precise as we want to be, we wouldn't have so much assuming. But as you guys will learn, engineering is all about assuming. The only thing that really changes is we always have to go and check our assumptions to make sure they're correct. So what I like to do for trusses, and this is going to be very, very important. So I'm going to erase this real quick. And I'm going to tell you my sign convention. So I'll write this down because this is the one thing that you guys are going to want to remember. So for me, I always, and this will probably be pretty obvious, always assume member is in tension. So member is in tension. What does this mean? Well, this means that if I were to draw a particle equilibrium or a free body diagram of any one of these joints, all of my truss forces are always going to be pointing away. So real quick, what I'm going to do is I'm just going to draw a free body diagram at C. So this isn't going to be exactly C. We're not solving the question yet. I'm just going to show you guys what I mean. So if I had, actually let's do D for a second. So if I had D, this is point D right here. Well, I see that I have an external load coming in on it. So this load, we know its direction. So I'm not assuming tension for this. We actually know its direction. But for the other forces, if I were to draw a little line around point D, remember, it's just the same as particle equilibrium where I'm just going to draw that particle and anything I cut, I've replaced with a force. So if I were to look at this real quick, I'll highlight it. I cut it 1, 2, 3 times. So I'm going to have 3 forces on here for the members. So I'm going to have one going straight up. So again, I'm going to put it straight up and I'm going to assume it's in tension. I'm going to have one coming in at an angle like this. And then I'm going to have one coming out to the side like this. So here's the thing. I have 3 forces now, which I'll just call A, B, and C. And I'm always assuming that they are in tension. Why do I do this? Well, there's going to be a couple things. One is if you have a very good sign convention, you're going to mess up very, very little. Sign convention is going to be the most critical thing to you guys in trusses because 2D particle equilibrium, you guys are experts at. You guys have done this before. It's 2D. You guys will never see a 3D truss in this scenario, which is very, very nice. You guys will never see a 3D truss on the final or anything like that. But here's where it's going to get kind of important, and that is think of support reactions. If I had a support reaction, and let's just go to this side real quick, and let's say I had a roller on a beam. And again, for me, I always assume it's going up. And let's just call this reaction Y. And if I do my sum of the forces, blah, 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 sum of the forces in Y equals 0. And I get Ry is equal to negative 10 kilonewtons. Well, what that means is that Ry is not going up. It means that Ry is actually going downwards. So when I were to state Ry as a final answer, as you guys know, I'd go Ry is equal to 10 kilonewtons downwards. Now, here's the problem that a lot of you guys are going to have. When we're analyzing a joint in a beam, the joints are connected at 2 ends. So let's take joint B. If I were to go to the other side here and draw a joint B on this side, it's going to have a force that comes out here because it's going to be the same as B. Remember, this force throughout this whole member there, that DB member, that's not going to change. So when I'm analyzing joint B, and I have that force and I'll have another force here, oops, let's try and make this look a little bit nicer to try and show my point, or else it's going to look pretty silly. So if I were to draw the free body diagram at B, I'm going to have this. And that force at B in one diagram is going to be equal to the force at B in the second diagram. But here's what's going to happen. Let's say that we're analyzing joint D, and I go sum of the forces in X, it doesn't matter which one, is equal to 0, so I do some sort of equilibrium, and I find that B is equal to negative 10 kilonewtons. Well, here's the thing about my sign convention. I assumed that B was positive, but I got a negative answer. So what that means is B is actually in compression. So my answer will be 10 kilonewtons. So, and then I had to put a C for compression. So this would be my answer. But here's the problem that a lot of you guys will do, is you guys will look at joint D and say, okay, well, I did B, it's in compression. But when you guys move on to joint B, so when we move on to this joint over here, what you guys are going to do is, okay, this is actually like this. And you guys will switch it. Now, I told my class this, and I'm going to tell you guys this. Don't do that. That will lead to a lot of mistakes. A lot of mistakes. So please do not do that. What you're going to want to do is you're going to want to keep it always in tension. So even though you already know that this is actually going the other way, don't switch it. Don't switch it. If I were to do sum of the forces in y equals 0, and I know that if I was looking at joint B, sum of the forces in y, well, I'm going to have some component of B. So it's going to be negative since B is going downwards. So right here, B is going downwards. So I'm going to have negative and then times some component of B. But when I enter this, I'm going to go negative and then it's going to be some components. And then when I enter B, I'm going to put negative 10. That's what you do. So we know what's actually in compression, but we're not going to switch anything. What we're going to do is when we sub in our answer for B, we're going to put its actual value, which was negative 10, which we found. So keep everything in tension, and when you're subbing in values, always use the actual value that you got before. And now this may sound a little confusing, I agree, but when we start going through the actual examples, it'll hopefully make much more sense. So I'm going to leave this here, and now we're going to start to actually look at the actual example. So I'm going to erase some of the crap around it, like this, and we're going to go. So here's kind of a fun fact, and this example is a little bit special, as you guys will see, and there's a very specific reason why it's special. It's because of its boundary conditions, or its support reactions. If I look at B, B is a pin. So it's going to have, oh, that did not come out the way I wanted it to. So it's going to have two reactions. It's going to have a vertical, and it's going to have a horizontal. So something like that. If I look down at A, oh, A is also a pin. So it's going to have two reactions. So horizontal and a vertical. So like this. And if I look, that's 4 reactions, but we only have 3 equilibrium equations. So in this case, we actually cannot solve for any of the support reactions. Or we can solve for some, but we can't solve for all of them. So what do we do? Well, this question came from an Eng 130 textbook, so it must be solvable. What do we do? And this is where I said, when we're looking at joints, we can do any joint we want. Any joint we want, as long as we have enough equations to solve for the unknowns. So if I were to look at, and I'm going to do this in a red highlight, if I were to look at joint D down here, okay, well, I know that the most I can solve for is 2. I got 2 equilibrium equations, sum of the forces in X, sum of the forces in Y. So if I look at my number of unknowns, it will be 1, 2, 3 unknowns. So if I look at this joint D, I can't solve for anything yet. I don't have enough equilibrium equations. So joint D, it's a definite no. If I look at joint A on this side, well, if I look at unknowns, I'll have 1, 2, 3. So joint A, that's not going to work either. So I'm going to erase those 3. What about joint C? So if I look at joint C, remember, the most I could solve for is 2 unknowns. Well, I got P. Oh, but I already know P. It's 20. So that's okay. So for unknowns, I have 1, 2. Oh, 2 unknowns. I have 2 equations. At this point right now, I can solve for joint C, which is actually very nice, because what this means is I can start solving for stuff even though I don't know the support conditions. Now, with that being said, I'm going to tell you guys this is a very special would probably be the best word, special case. Usually what you're going to see is the first joint that you're going to solve for is going to have to be a joint with support conditions. That's why when I say we're dealing with trusses, you're going to have to know support conditions, because usually that's going to be the first joint you solve for. Usually in these kind of cases, this is just a special case. If I were to actually go back really quick and go to the next example and look over here, well, it's actually pretty much the same. So this one doesn't work. So let's go even further. Let's go to this one. So if we look at this diagram, there's actually not a single joint we can analyze right from the beginning unless it's joint F or joint A, because those are the only ones that only have 2 members on them. Those are the only ones that only have 2 members. If we look at the rest, they're having more than 2. More than 2, that's not good. So in order to solve for those joints, well, we're going to actually have to know the support reactions at those joints. So like I said, even though this is a nice case where we don't have to go to the support reactions, this is very rarely happens. It just so happened to happen in this example. So for this example, we're not going to worry about it. But as we said, joint C right here, we're actually good to go. So I'm going to draw a free body diagram of joint C. So every time you're doing a method of joints and you're analyzing a joint, you're not going to like this, but we're going to have to do a free body diagram. So what I'm going to do is I'm going to come down here. I'm going to say, okay, well, I'm going to analyze joint C. So I put joint C. And over here, I'm going to draw my free body diagram. So I got my joint right here, which is C. If I look up, I have an external force of 20 kilonewtons going downwards. So right here, I'm going to have an external force of 20 kilonewtons going downwards. So this is going to be 20 kilonewtons. And we know that we cut through 2 members. So the first one's going to be CB. So this member right here. So you can call it CB or you can call it BC. They're going to be the exact same. So if I come down here, we know that we're going to have a member called BC. Or remember CB, that also works. And remember, when we cut through these members, we're always going to assume it's in tension. So we're going to have this pointed outwards. If I come back up here, we see that we cut through a second member, which is this one right here, which we're going to call CD. And this one is perfectly vertical. So this one's just going to come straight down. Remember, we're going to assume it's in tension. And this one's going to be, I believe, CD. And I'm just going to double check real quick. It is CD. So this is my first joint. As we can see, this is actually a very, very nice joint. Because if I were to do some of the forces real quick, and X is equal to 0, well, looking at the equation, I got BC going in the X direction. So we're going to have BC, and that's it. So what does that mean? Well, remember, the equation has to always equal 0. So that's the answer. BC is actually equal to 0. So if I come to the side here, I'm going to write BC is equal to 0 kilonewtons. And as you guys will see later on, we actually have tricks that we can determine these members really, really fast without having to do any sort of equilibrium or anything like that. And that trick will actually be a very important part of your final, because what they like to do, because trusses, as you guys are seeing, they're pretty easy. They're nothing crazy. But if we give you a truss with a lot of members, well, it's going to overwhelm you. And that's what they kind of go for. It's actually the same as force reduction. Force reduction is not that hard. Or taking the moments of a force, not that hard. But if we give you 6 forces and you have to take, let's say, the cross product 6 times, that sucks. And no one wants to do that. And it's kind of the same here. We can get rid of a lot of those members. Just like how when we had 6 forces in the, let's say, a midterm scenario, a lot of them will cancel out, or a lot of them won't create a moment, stuff like that. This is kind of the same methodology, except for trusses. So we can move on. We did some of the forces in X. So now we can do some of the forces in Y is equal to 0. So looking at this equation, well, we got 20 kilonewtons, but it's going downwards. So we're going to have minus 20. And then we got CD. And CD is also going downwards. So we're going to have minus CD. And this equilibrium, so everything must equal 0. And if we do that, what we get over here is CD is equal to negative 20 kilonewtons. So now we have to say, okay, we assumed it's in tension, but we got a negative answer. Well, what does that mean? It means that CD, so when I'm stating my answer, is equal to 20 kilonewtons, but it's going to be in compression because we assumed tension but got a negative answer. So this one must be in compression. So I'm going to put a box around this and we're good to go. So now we know CD and CB. So what I'm going to do is I'm going to just erase some of this stuff on the truss real quick. So now if I'm looking at the truss, I already know this and I now know this. So there's only actually 2 more members left. So now I'm going to move down to joint D. So I'm going to highlight D. And remember, we couldn't solve this one before. We had too many unknowns. So let's just check again now. Well, P2, we know. But we don't know BD, we don't know AD, and before we didn't know CD. But now we actually know CD. We know it's 20 kilonewtons in compression. So now we only actually have two unknowns at that joint. So we can solve for this joint. So what we're going to do is we're going to come down here. Just like before, we're going to do joint D. So we're going to state which joint we're looking at. And I'm going to draw the free body diagram at that joint. So I'm going to put the joint as right here. We know that we had a force coming in on it of 10 kilonewtons. If we look up, we see at the very, very bottom of the joint going horizontal is AD. So from here we have another member force coming out. So it's going to be like this. This one's going to be AD. If we look above AD, we have a diagonal member, BD. So what we're going to do is we're going to draw a diagonal member. So again, we're assuming all of these are in tension. So this one's going to be BD. And since it's diagonal, what we should also do is put its relationship for its angle. So trusses are actually going to be a very peculiar case for you guys. Very, very rarely will you guys see an angle in degrees. So what we're going to do is we're going to use the triangle. And how we do that is we actually just look at the horizontal span of the member and the vertical span. So if I look at DB, we see that it goes 2 meters horizontally and 1.5 meters vertically. What does that mean? Well, when I go to this little triangle down here, we know it goes 1.5 vertical and 2 horizontally. And then from there, we can easily find the hypotenuse of this. Alrighty, so we got our two unknowns, but now we also have to include CD. So right here, we know we have force CD. So I'm just going to put it like this. And this one's going to be CD. But now here's the thing. And this is what I was trying to tell you before. So hopefully this will make more sense now. So CD, we assumed was in tension before earlier, as we see right there, but it was actually in compression. So CD is actually going like this. It's actually going like that. But I told you guys, and I hope this is what you remember, please do not do this. Always assume it's going in tension. So we know that it's actually not in tension right now, but we're going to assume it is in tension. So we're going to still assume tension. But when we put in the value, we're going to put in the exact value that we found. So looking up here, we knew that CD is equal to negative 20. So right here, I'm going to put negative 20 kilonewtons. And the fact that we have that little negative in there, that's accounting for its actual direction. So that's the best way to do trusses. This way will guarantee you that nothing will go wrong, which is exactly what we want. One little sign can change everything. If you guys wanted, now I'm going to tell you this even though I don't recommend it. If you guys are absolutely saying, okay, well, I hate that method, Clayton. I want to put its actual direction. That's fine. You can do that. But here's the thing that you're going to have to do. And a lot of people will change it, but they won't change CD. If you're doing that, you must, and I mean you must, get rid of the negative up here. It must just be equal to 20. So that's why I don't do it, because it's easy to change the arrow, but a lot of students will forget to take away the negative inside of that. So that's why I prefer just to keep it as okay. It's still, we'll keep it as tension, and we're just going to keep the actual value that we found, which is the negative 20. So this right here is going to be my free body diagram. And if I look, I can, two unknowns, two equations, and now it's just picking which equation is best to start with. So if I were to do sum of the forces in X right now, well, AD has a component in X, which is all of AD, and BD also has a component of X. So if I do that equation, I still have two unknowns. So that one's probably not the best. But if I were to do sum of the forces in Y is equal to 0, well, only BD has a component of Y. AD doesn't. So my equation will have only one unknown. If it's only one unknown, I can easily solve for it. So looking down here, if I'm doing sum of the forces in Y, I got CD going upwards. So it's going to be CD, and then there's going to be BD, which is also going upwards. So plus BD. But remember, it's only a component of BD. So what we're going to do is we're going to take the horizontal component of BD, or sorry, the vertical, which is the 1.5 right here. So we're going to have 1.5, and we're going to divide that by the hypotenuse of that triangle. So even though it's not stated on here, I can actually calculate it very easily, and we get that this hypotenuse is going to be the root of 6.25, like that. So this is going to be 1.5 over the root of 6.25. And if we look for vertical, well, that's it. It's just going to have those two components. So I can put that this is equal to 0. But if we look right now, well, it's not helping too much because we still have two unknowns, CD and BD. Well, we actually know that CD is going to be equal to negative 20, because that's its actual value. And then plus BD times 1.5 divided by the root of 6.25. And we know that all this is equal to 0. So now the only thing left is BD. So when we solve for this, we get BD is equal to 33.3333 repeating kilonewtons. So since it's a positive answer, we know that BD is going to be 33.3 kilonewtons in tension. So it's very nice. We can highlight that. We're good to go. Perfect. My boxes are getting much better. So now, if I look at my equilibrium, my free body diagram, well, BD I now know. So my only unknown is AD. So now I can go to my second equation, which is going to be the summation of the forces in the X is equal to 0. So looking at this, what I'm going to have is I got 10 kilonewtons going to the right, so that's going to be positive. So I'm going to have 10 kilonewtons. Actually, I'm not going to put kilonewtons. I don't know why I did that. So I have 10 going to the right, so it's positive. I have AD also going to the right, so we're going to have plus AD. And we're going to plus, and if we look, we see that BD also has a horizontal component. So I'm going to take its component by going 2 divided by the root of 6.25. And then it's going to be that times BD. And if we look at BD, we know it's 33.333.3 repeating. And this must all equal 0 because it's in equilibrium. Well, now I look, AD is the only thing I have left. If I were to go down here and just solve for AD, what I get is AD is equal to negative 36.66 repeating kilonewtons. So I assumed it was in tension. We got a negative answer. What that means is AD is equal to 36.7 kilonewtons in compression. So since it was negative, we know that it's actually in compression. So I'm going to draw a box around this answer. And if I look up to my diagram now, so I'm going to erase the kind of these little things right here. And I'm go back to my highlighter, which is hopefully still, nope, it's in red. I now know BD and I now know AD. So if I look at this truss, I solved every single member, which is what the question would like us to do. It also says it wants it in tension or compression. So I just look real quick. I have it labeled as compression, tension, compression. The only one I don't is when it's equal to 0. That's okay because it's not going to be doing anything. But yeah, so that is this question. So it's not bad. The cool thing here with the method of joints is you don't have to find a support reaction if you don't need it. But like I said, usually in the final, you're going to need it. So although this question was nice, you didn't need it, be prepared. But if that was the case, that's easy because if let's say that this was just a roller. Actually, it'd be this one. So let's say that A was a roller. So this one's just going to have one right here. We can solve for both of those. So let's just say for fun that we had 10 kilonewtons and 15 kilonewtons for those support reactions. And if we were to look at that joint now, my only unknowns are going to be BD and BC. So I can actually start at joint B and solve for those ones, stuff like that. So the method of joints, it's really just about trying to figure out, okay, which joint do I start at? For an exam type scenario, usually what's going to happen is they're going to give you a truss that's going to be something crazy. Like, let's say this. This is actually probably a good one. And what they'll do is they're going to ask you for specific members. There's no way in an exam scenario they would ask you to solve for absolutely everything in this truss. What they'll probably do is they're going to say, okay, tell us this joint and this joint, so FE and FG, and then tell us HI, IC, and IB, or CB. So they'll usually give you two kind of sections. And what you guys will find is one of the sections is going to be near a support. So if we look at this section right here, it's near a support. So what you're going to do is you're going to find the support conditions. You're going to say, okay, well, now I know this force right here. If I know that force, I can analyze joint F and find those other two forces. So that'll be good to go. Now the second method's a bit more tedious, because if I'm doing the method of joints, I'm going to have to start at A and find these two. And then I'll have to move up to, let's say, B, and then find these two. And then move to I to find these two. So it gets kind of really, really tedious. But as you guys will learn, is we have a second method specifically for this scenario where we're trying to find a bunch of member forces that are kind of in the middle of a truss or not near a joint. And we'll cover that a little bit later. The title here kind of gives it away, is the method of sections. So you guys will see. All right, so I think that's it for this video. Again, if you guys are still a little bit shaky on the method of joints, we have another example coming up where we're going to go through a truss with a little bit more members to show you, to hopefully show you guys exactly what to do. So thank you all so much for listening, and I'll see you guys in the next video.